Hi everyone, welcome back to our channel. In today's video, we will be showing you how to create a topology and mesh on a Venturi Injector. Introduction. A Venturi Injector works by creating a pressure difference between the inlet port and outlet port. This pressure difference is created as the liquid speeds up as it passes through the throat. The pressure drop causes a vacuum to be created below in the suction port, which causes another liquid to be sucked and injected into the flow. CAD Panel. The CAD model of the Venturi has to be imported and converted into GridPro's native.tria format. The IGS file is imported into GridPro and meshed using the inbuilt surface mesher. The surface mesh on the CAD model with the specified parameter looks to have captured the geometry well. The surfaces can now be loaded into the topology panel. Since the whole model is exported as a single surface, the surface needs to be split before the topology can be built using it. This is done using the split option in the surface panel. The surface is split on all its sharp edges, and now we have an inlet, outlet, venturi, and suction port surface. Topology. There are several different ways the topology can be built for this case. We will show you three such ways: by using a top-down approach, by using the whole topology feature, by creating a 3D topology from a 2D section. Top-down approach. We are starting by creating a box macro wireframe around the visible surfaces. We then add inserts to create blocks around the suction port. Now we are deleting the blocks which are outside of the fluid domain. The corners are now being repositioned using the edge length option. This gives the grid smoother a much better initial positioning, which speeds up the grid smoothing process. Some additional inserts are being added, which will help us later on to exclude the block faces while creating the O-grid. Hole topology. GridPro has some macro block building tools, such as the hole topology tool that creates blocks around any geometry where a circular opening opens into a larger domain. Using this tool, the wireframe for the suction port and the hole is being created automatically. The tool needs a few inputs to be specified, like the top surface, bottom surface, and hole surface group. The output wireframe has to be extended to create the blocking for the inlet and outlet port. Revolving a 2D topology. First, a 2D blocking is being created along the cross section as shown. A 3D blocking with core blocks is then automatically generated using the revolve feature. Here, we see that the circular with core option creates the blocks in the central core region of the venturi. We now have to create a blocking for the suction port. This is done by extruding the block faces in the throat of the venturi. Once we have created the initial topology using any of the three approaches, we need to follow the steps ahead which are common to all approaches. Wrapping. We now group the outer shell of the geometry which is used to create the O-grid structure for the current blocking. The O-grid ensures that block orthogonality is maintained around all surfaces. Wrapping the corner group creates the O-grid blocking structure we need. Assignments. The corners now need to be assigned to their respective surfaces. This is done using the generic tool. A few additional inserts are being added as required and repositioned. The second insert added here is to better deal with the curvature of the inlet port. Resolving the mildly severe singularity. Checking the validity, we see that there is a mildly severe singularity at the suction port throat intersection. To understand about mildly severe singularities, check out our video here. Note, the whole topology tool takes care of this part automatically. To resolve this, we are creating an internal surface using the internal surface tool. Now we are assigning all the mildly severe block faces to the internal surface. The internal surface constrains these block faces onto the surface, and the smoother will have a much better time in generating the grid with the aid of the internal surface, which acts as a guiding surface for these block faces. The same block faces are then internally wrapped to create a valid topology. The internal wrap creates an O-grid structure around the outside of the suction port, without which there would be a 3-point singularity on the surface of the suction port. The densities are then adjusted according to the lengths of the blocks. Assessing the grid. A high-quality structured mesh is generated after running the grid smoother. Looking at the cross-section, we see that the intersection of the suction port with the throat is captured accurately, courtesy the internal surface present there. A quick quality check also reveals a low skewness in the grid, which provides for more accurate CFD results. Thank you for watching. If you like this video, leave us a like and subscribe to the channel for more videos. If you have any questions or any comments, feel free to leave it below. Follow us on our social media pages. Links are posted in the description.